Record. Okay, so again, we'll have the paper. Actually, I don't remember what this really is going to be hard. I'm gonna have to figure something out because this is not viable. There it is. So the first paper is for you guys to. I reduced the size of the paper itself. It's literally just a single spaced New Courier font 12, one page. So basically just fill up a page with information about a biologically active molecule. Do we know what that phrase means?
Active in the body or what?
It'll interact with your biology in some manner. Most of the molecules in the universe have no impact on your body. You would just poop them out. Like your body can't do anything to them. So find a biologically active molecule. It could be something as simple as aspirin, or you could go off and find something interesting. I mean, I don't care if it's a beneficial, if it's nutrition, if it's a poison, whatever. Just find a biologically active molecule, then get 3 sources and write a page about it. So this one's shorter because I have you do this other paper as well. And this one is actually even shorter. It's just a paragraph and then some bullet point topics. So this is because of the nuclear aspect. And so it's 88 minutes long. So just watch this. It's pretty amazing, actually. I mean, it's the cinematography, the editing and whatnot isn't all that great. It's just that they have put together these clips from things. Do you know what the attitude was in the US, generally speaking, for safety in the 50s and 60s? Like what kinds of things were going through people's minds? So World War II is over. Nazis are gone. We enter the Korean War. But what are we most afraid of? We're talking about 30 years of people who are just plain off scared that at any moment a nuke could drop on their head. So there's this paranoia, and it's super peculiar how some people freak out about it and they do everything they can to try to protect themselves. And then other people just, whatever is what it is. And so there are these clips from popular culture, videos that the military let go. Like sometime in the late 70s, there was a Freedom of Information Act. It wasn't called that, but it's the same situation, where the military released videos of things that had happened while we were making the nuclear bomb and when we dropped the nuclear bomb, a bunch of video stuff that wasn't available to the public. And so these people got all of this stuff, these historians and videographers, and they put it together and made this little thing called the Atomic Cafe. And you'll watch it and be like, there's no way people actually thought that, when they actually totally thought that. Then everything else with the homework is the same. The postings are the same. The labs, the same. Quizzes are the same. Exams are the same. Did I change those? I did. Okay. And I have all the due dates ready to go correctly. So you can also, I mean, again, you can either look at the due dates like inside of like here and whatnot, or you can go over to the calendar to make sure you know when stuff's due. Let's see, gonna. Okay. So the difference from this one to the next, from the previous classes, is we're going to be talking about acids and bases, and then we're going to talk about ionic equilibrium and then free energy. So that section that term Gibbs free energy that we never really talked about, but it was part of some of the thermal or some of the kinetic stuff. So free energy and thermodynamics is one thing. We'll talk about electrochemistry, batteries and whatnot. Then radiological activity, so things that are radioactive and nuclear chemistry, and then at the end we'll talk about organic chemistry. Do you guys remember? I mean, we were just talking about it briefly, but what my grad school concentration was? No, my what we concentrate. What was our subject matter?
Oh.
The best parking on campus is for who? The nuclear chemists. So my grad stuff in grad school was all about nuclear chemistry. Does anybody remember what I did in the Navy? No, aircraft carrier, no submarines, but reactor. Yeah. So I maintained all the electrical equipment on #1 nuclear power plant on the Roosevelt. So all of this nuclear stuff is, that's my favorite part of this, is talking about this stuff because I know all the theory stuff and then I've actually used it. I don't think anything in here is any different other than the second paper, the video paper. There's only one holiday. It'll be Memorial Day on the 27th. So we'll actually have 21 class periods. Same situation, 3 exams, withdraw on Friday if you need out. And that's really need your nothing. Okay. Does anybody have any syllabus questions or? Everything is the same. Again, with the exception of that, there's one extra paper. So we're going to talk about acids and bases. Why is this taking so long to open? That was weird. Okay. Did it just open 3 copies? Is that what just happened? No. There. All right. So when people think about chemistry, acids and bases are one of the things they think about. We're just finally now getting to it. So the first person that came up with an idea to classify some molecules as acids or bases is this guy named Arrhenius. Swedish, British or Swedish. And his idea came from, he was trying to come up with dyes for clothing. That was a really big, that was a market. One of the most marketable ways that a chemist could make money for themselves is to figure out new ways to color clothing. Because if like regular people just had gray, brown clothing, whatever the animal's hide was, that fur was, you were kind of stuck with that. Do we know what expensive colors were? Blue was kind of expensive as far as dyes go. Do we know what the most expensive one? Yeah. Purple. Purple is the royal color because it was so hard to get a purple dye that the only people that could afford it were royalty. So that's why purple gets classified with royalty. So he was trying to come up with a purple dye that was affordable. And so where do you think people get dyes from? Okay, so basically plants. That's the first place everybody looks is fruit, not fruit per se, but plants. So can you think of something that's purple? Yeah, flowers are harder though because they're difficult to harvest, and there usually isn't very much dye in them because there isn't much matter.
Some berry would have a light.
Yeah, we're looking for that like deep purple. And you're going to be like, oh yeah, that's where it is. Something you probably don't eat much of, although it's probably really good for you. Well, I know it's really good for you.
What?
No, that's all true, but not blackberries. Blackberries were not a common thing, which is weird because of where we live, which is also weird because they're not from here. They're from Europe and they got here and we're like, we're home. Let's take over the whole state.
Maybe a root.
Cabbage. Purple cabbage. That's the color they were looking for. So Arrhenius is like, can I pull this out? Can I make this color fast? Because that was the problem. The issue is you could pull the purple out and you attach it to clothing and then it would wash away. So you needed to be color fast. So he was trying to come up with a way to color fast the purple to mostly wool and cotton. So in doing this, he actually figured out a way to classify acids and bases. This is the most common way to classify acids and bases. It's not the most extensive. It's not the best way, but it will serve you. So we're going to find that we're going to have 3 different theories of acids and bases, and all of them have use. And this is the first thing that most chemists think about when we're talking about acids and bases, even though it's not technically what's going on. It's just an easy way to think about it. So when we were talking about the structure of the atom, and Bohr had his model, and it's really easy to think about Bohr's model because you can immediately visualize the solar system. Same kind of setup. And the idea that Heisenberg's theory came from, you know, the multiple layers of that statistical model isn't as easy for people to think about. But they're both useful, even though the first one, the Bohr model, isn't exactly what's going on. So this isn't exactly what's going on, but this is super useful, and you can think about this in almost all circumstances, and it works. All right, so wait, there's a delta there? That's not supposed to be there. Cabbage a leaf? I guess so.
Just like a root.
Okay, so anything that produces hydrogen ions in water is going to be classified under this as an acid, and anything that produces hydroxides ions in water, that's going to be considered a base. So it doesn't even have to have H's in it or OH's in it, the thing that I add to the water. If the number of H pluses in the water goes up, or the number of OH minuses in the water goes up, whatever I added to it was an acid or a base, depending on which one. So that's kind of something that people need to get their head around. So if the thing that I add to the water doesn't have any H pluses, any H's on it at all, how can the H plus ion concentration go up in the water? The water molecule itself is H's and OH's. So if I put something into the water and the thing yanked the water molecule apart to produce H pluses and increase those concentrations, that thing is an acid. And then the exact opposite happens with the base. If I put this thing into water and all of a sudden OH's are there because a water molecule got torn apart, then I've got excess OH's, and so I've got a base. So here are like the 2 most basic examples. Hydrochloric acid, so stomach acid. When that goes into water, it separates into H pluses and Cl minuses. And so obviously I've increased the H plus ion concentration because I just added H pluses to it. What do we know about the solubility of hydrochloric acid? Is it soluble? So those memorized rules are totally going to still apply to this class. So the list of solubility rules, that first one was group 1 metals and ammonia compounds are always soluble. Do anybody remember what rule 2 was? Acids are soluble. So this will be, we'll get more specific about hydrochloric acid itself, but hydrochloric acid is soluble. So it goes into water, it separates into H's and Cl's. The next one, somebody want to give me a name for that? NaOH? That's sodium hydroxide. So when that goes into water, what's it going to do? Well, when the NaOH solid hits water, what happens to it? Disassociates, fully soluble. How come it's fully soluble? Because rule number 6 says hydroxides are insoluble. Sodium's rule number 1, so it doesn't matter what the hydroxide wants to do. The moment this touches water, they separate. This is the active ingredient in Drano. You guys have used this a couple of times, and you'll use it again today. So these two things are fully soluble. They go into water. The hydrochloric acid raises the H plus ion concentration because it's literally adding H pluses to the water. And then when the sodium hydroxide hits water, it separates into NAs and OHs. And in this case, the Cl is a spectator ion and the Na is a spectator ion. During this process, they don't do any reacting. They just stay soluble and aqueous in the solution. And the OH minus concentration has gone up. So since that has gone up, then the NaOH is a base, the most basic of bases. All right, so we got this first rule that simply says if H pluses go up, it's an acid. If OH minuses go up, it's a base. That's it. That's Arrhenius's rule. And again, it will be probably the most useful to you. The next one we're going to talk about is Bronsted-Lowry. These guys don't know each other. This doesn't happen very often in science, but it did happen here. At the exact same time, these two guys, the same month, published their results of an acid-base theory that was a little more inclusive, I guess would be the best word, than the Arrhenius definition, and also fixed a problem with the Arrhenius definition. So since both these guys published at the same time, they didn't know who to give the credit to. Like Arrhenius didn't have anybody fighting him for his theory. These two guys were like, all right, I guess we'll just share it. So now this is two totally different people from two totally different countries that didn't know each other that ended up producing this theory. And so what their idea is, the first thing we need to talk about with their idea is that the water molecule itself can separate itself. When two water molecules run into each other in just the right way, you will get one of the H's leaving the one of those water molecules and attaching itself to the other water molecule. So we end up with this OH3 plus and then OH minus. So I don't like the setup at all. Yes. Should have tried to do that before. One is and my pen's gone. Paint. Where is the screen? So I have this third screen here and I have no idea where it is in relationship to the others. Display.
Like there's 3 screens, not 2.
No, I do have 3 screens here now. All right, but it was like way over there on the other side of that screen. I just had to move it. I definitely didn't want that. All right, so there we go. So awesome, nothing's working. We What? Why is it drawing over there? All right, whatever. I'll see if I can do that. Probably not. Oh no, it worked. All right, this is weird. All right, so this thing called the hydronium ion is one of the keys to the Bronsted-Lowry definition. So what Bronsted-Lowry had said was this can't exist in water by itself. I can't have H pluses just floating around. It doesn't make any sense. Does anybody have any idea why it doesn't make any sense? So the water molecule looks like this, right? That molecule with the O's, with the O at the bottom and having two lone pairs of electrons. So those two lone pairs of electrons that's a lot of negativity. And this H plus, what is an H plus? Like fundamentally, what's another way you could describe H plus? It's simply a proton. It's the smallest positive thing in the universe. So this proton is floating around in the water freely, and the water molecule wouldn't have that. It's because this entire section of the water molecule down here, this is all negative down here. And if it were to see this thing, it just attaches itself to it. So it literally makes like a temporary polyatomic ion. You actually get, it's going to drive me bonkers. You get a tetrahedral molecule with a lone pair of electrons on it. So the Bronsted and Lowry both came to this conclusion that you couldn't have H pluses floating around. It would bond with the water molecule, making this hydronium ion. So this is going to cause confusion in this class and with people in general who aren't super schooled on it. These two things will be synonymous with each other, H3O plus and O and H plus. Now, what I need you to remember is H pluses don't exist, but I'm going to write it. You're going to see it in the textbook. You're going to see it in the notes. You'll see it on a homework, quizzes, exams. And in your head, you got to be thinking, okay, so that's not a real thing. It's H3O plus. It's just the way things are going to be. So their idea that this, oh my God, that doesn't happen. So why would a molecule spontaneously let go of its bond? So what we're talking about is an H bonded to a Cl. So when we were talking about sodium chloride, or in this case, sodium hydroxide, how does it separate? What was the idea of the dissolution of the molecules? When it dissolves, what happens?
Sodium chloride?
For anything that dissolves, what's going on? Anything that's soluble. Do you remember that short clip that I put on that showed the dissolving of table salt? It was a crystal matrix lattice structure.
Oh, the one molecule.
Yeah, the different charges on the water molecule grabbed either the sodium on the oxygen side or the chlorines on the hydrogen side and pulled them apart. So they pulled the thing apart. So if I want the H and the Cl to disassociate with each other, is there an energy input? Yes. They're connected to each other by a chemical bond. So what do I need to do to the chemical bond? I need to break it. So the first thing I need to do is I need to break the bond between the H and the Cl. And so what Bronsted and Lowry were both saying is this doesn't just go in water and they just let go of each other. Something has to pull them apart. They have to be yanked apart. And so it's the water molecules that do the pulling apart So this bond takes a little bit of energy, and then what you end up with are CLs that are surrounded by water molecules, hydrogen sides. But no bond forms. It's just it was just like a loose ionic connection. This is positive, and this has got a sorry, the chlorine's minus charge, and the hydrogens have a partial positive on them. So they're just next to each other because their associated charges are opposite. On the other hand, though, it forms an actual bond with the water molecule because it can. And when we move on to the third idea of what acids and bases are, this will become even more clear. So Bronson and Lowry are basically saying that this water molecule becomes a charged particle with a +1 charge because it took on a proton, but not a proton into the nucleus, a proton that it's chemically bonded to. The whole thing becomes +1 charge, and we're going to give it a new name. We're going to call it the hydronium ion. So hydronium is H3O plus, but again, you will see H plus written. And when you're thinking about that H plus, I need you to remember that that doesn't exist. It's really a hydronium ion. This is if considering if we're talking about water molecules. So we still haven't gotten to the definition. So what their actual definition was that anything that donates a proton is an acid, and anything that accepts a proton is a base. So we're no longer talking about increasing or decreasing OH concentrations, OH minus concentrations, or H plus ion concentrations. So here's an example of a Bronson-Lowry acid reaction. So I've got nitric acid, and nitric acid is soluble. Nitric acid interacts with the water molecule, and then you produce a hydronium ion and the nitrate. So the nitric acid loses its H, the water molecule grabs the H, and then what you're left with is that nitrate polyatomic ion. So in this case, I don't have just an acid separating into its two component ions. I have something come in and reacting with it, pulling the thing apart. So I get the water molecule accepting an H plus. So that means it's accepting a proton. So anything that accepts a proton, what did Bronsted and Lowry call that thing? If you accepted the H plus. That's base. And so obviously the nitric acid is the acid, but why is it the acid? What's their definition saying? It donated an H plus. Okay, so that's why the nitric acid is an acid in their theory, and the water molecule in this case is a base. Water can be an acid or a base, totally depends on its situation. Water's a little bit like carbon with its electrons, where if the carbon comes across something that wants to give electrons away, it will accept the electrons. If it runs into something that wants electrons, it will give those electrons away. So the water molecule is accepting of H pluses. In this case, the nitric acid wants to give an H plus away, so it accepts it. If it comes in contact with the base, it's fine donating an H plus and becoming the acid. So it's totally situational. All right, so here's another example. The first one is ammonia, and then here's my water molecule. And what's happening is the nitrogen has that lone pair of electrons on it, and it can offer up those lone pair of electrons to be a place for the H plus to attach itself to. And on the other side, I've got an H plus ion, and then I've got an NH4 ion, so the ammonium ion. So who's the acid and who's the base in this situation? The acid is the water. It donated an H plus. And so that makes the ammonia the base because it accepted the H plus, accepted the protein. So you just need to follow the H and for Bronsted-Lowry, and that will tell you who the acid is and who the base is.
Contextual.
100% contextual. You need to look at the situation and determine what's going on to be able to assign classifications to molecules. Okay, so this first one here is a very classic reaction. Do we understand why I have the net ionic equation? So the first one is the molecular equation. And then the next one is the net ionic equation. I had fully skipped the full ionic equation. When the HBr goes into water, it says aqueous there. So it separates into H plus and Br. The OH, NaOH goes into water, it separates. And then those components are able to bump into each other and form a compound or not form a compound. Sodium bromide isn't going to form a compound, but the water molecule will be formed. So the sodium bromide is a spectator substance. The sodium and the bromine are spectators, so they get removed. So my net ionic equation, the thing that I made, is water molecules. So when you mix an acid and a base together, you're going to get water and a salt. Why? Because I've got an acid that's an H plus and an anion. Got a base that's in this case an Na plus and an OH. And so when they all separate out, the H and the OH come together to make a water molecule, and then I'm just left with NAs and BRs, and so I get salt. So if you you get sick, you vomit, what would be a good way to make it so your esophagus is no longer hurting? No, not salt water. You want to make salt water. You want the acid that's irritating your esophagus to not be acid anymore. So how could I not make it acid anymore? What did we just say happens when you mix an acid and a base together? Makes water and salt. So in your esophagus, you've got an acid irritating all those cells. So what should you be swallowing? Something basic, something not too basic. Like, I'm not suggesting, oh, I vomited, I'm going to go take a swig of Drano. That's not going to work for you, because the Drano will do a lot of damage on its way down. Once it gets there, it's like, yeah, great. If you could like spray it directly onto the esophagus, it would be super useful, but obviously you can't do that. So what you would like to do is consume a base that won't irritate anything on its way down. And so what would be a good thing to, what do people take when they have an upset stomach? Okay, so Pepto-Bismol, Tums, so things that are carbonates in them. Okay, so the carbonates, and more specifically hydrogen carbonates. And so the term for, do you remember what the old term was for hydrogen carbonate? Some of you, when I asked you to put names down for something like NaHCO, you'd put down sodium hydrogen carbonate, and some of you wrote sodium bicarbonate. Do you remember we were talking about that? The old nomenclature for the polyatomic ion HCO3 was bicarbonate. That was a term, that bi term was a term that they used to classify any polyatomic ion that had an H attached to it, and it was still an ion. But it's confusing because bi usually means two, and it's almost never two H's. So we try to get rid of that. But you'll still hear that term. If you got an upset stomach, take a bicarbonate. What they're telling you to do is take a hydrogen carbonate, something, a salt that has a hydrogen carbonate in it. So probably not sodium hydrogen carbonate. What's the common name for sodium hydrogen carbonate? It's in your kitchen. Probably. It's in your grandmother's kitchen, most certainly.
Baking soda.
Baking soda. Have you ever tasted baking soda? It just tastes like table salt. There's not, I mean, you wouldn't be able to differentiate them. You don't use the baking soda for salt, because if something that you're cooking has an acid in it, you're going to get a fizzy reaction and a different flavor. But you wouldn't want to take, you couldn't really do it. Like, it would be pretty damn hard for you to take a scoop of baking soda and actually swallowed it. I mean, imagine trying to take a spoonful of table salt. Like, you'd probably vomited it up. Your body's like, whoa, that's too much salt even for an American. So you want to do is take something that won't dissolve. unless it's in an acidic situation. So Tums, they can be calcium hydrogen carbonate, calcium carbonate, magnesium carbonate, and then the Pepto Bismol is bismuth and hydrogen carbonate. And so both of those things have a carbonate in them. And what we'll find is the carbonate is a really good acid or base, depending on the situation. That hydrogen carbonate is a lot like the water molecule. Depending on what's going on, it could accept the H plus or it could let go of the H plus to do whatever it needs to do. So if you take a Tums or Pepto Bismol, the HCO3 that goes down your throat is like, hey, look, there's excess H's. I'm going to grab those things and pull them off the esophagus. So like crunch up Tums in your mouth and swallow it, or even put it in water or something like that. That would be the best way, because as soon as you do that, then all the acid is not acid anymore. It turns into salt and water. So then you want to make sure that the salt that you're using is a good salt. So calcium salt would be a good thing, or magnesium salt. Those are good things. The sodium salt's not really what you need. Okay, so we've got two theories so far. We've got Arrhenius that just says if H plus goes up, it's an acid. If OH plus or minus goes up, it's a base. And then we've got Bronsted-Lowry that said, well, H pluses don't exist. And the idea that an acid or a base are just going to separate spontaneously isn't true. The water molecule comes in, does the separating. So we need to be more clear about what the actual bond breaking is. And so then we're going to change the definition to accepting or donating a proton. I don't just increase H pluses, I'm really increasing hydronium ion concentration. So when you feel that burning sensation in your back of your throat after drinking a soda, that's acid, that's hydronium ions interacting with those ions, possibly killing, or not ions, interacting with those nerve cells, probably killing them actually, because the acid concentration is so high immediately. Does anybody know how many acids are in a can of Coca-Cola? Phosphoric acid, citric acid, ascorbic acid, carbonic acid. Put like tarnished jewelry in a can of Coke and then pull it out a few hours later. Not tarnished anymore. You think about it, cleaning your interior. You know it's probably not awesome when you give it to someone who's never had one before and they immediately have diarrhea. So like someone who's never had a can of Coke will drink it and then be on the toilet for a while because, wow, that is a lot of acid. My body is not used to that. Okay, so the last person we're going to talk about, the last theory we're going to talk about of these three is the Lewis acid-base theory. This is the most general theory. The cool thing about the Lewis acid-base theory is it doesn't disprove the first two. It just makes the idea, like Arrhenius's idea of what an acid base is super narrow. And then it gets a little bit more broad when we talk about Bronsted-Lowry. And then you get to a situation with Lewis and it's like, oh, we didn't have a classification. Like we have all these different reaction types, like combination and decomposition and single replacement, double replacement, combustion. We didn't have a name for these reactions. And now Lewis has said, well, if we think about these things in an acid-base way, then we can classify all these as acid-base reactions. And they operate just like acid-base reactions. So let's do that. So Lewis, we've heard his name before. Does anybody remember where? Lewis, C. N. Lewis, that's the same guy, Lewis Structures, Lewis acid-base theory. So he's got every chemistry book he's in there at least 2 or 3 times. He's kind of a sad guy though. He had like 5 students win Nobel Prizes and he never won, and it made him really depressed, which I think is terrible. Like if you didn't win the Super Bowl, but your kid won the Super Bowl, you'd probably still be pretty damn happy, right? Well, he wasn't happy. He actually committed suicide in his lab. It wasn't technically a suicide, but there's no way a guy like him would have mixed the things that he mixed in that room with no breathing apparatus. Okay, so I want you to read this paragraph right here, this quoted paragraph. We are so. So these are Lewis's words. What's he trying to say?
The context of F-way solutions.
That we think about water too much. That there are lots of chemical reactions that don't happen in water that are still acid-base reactions. You guys did one. You did for sure. You did not. You did not.
Which one is this?
The reaction that he did that you guys didn't do is in the vent hood, you had concentrated hydrochloric acid at 12 molar and concentrated ammonium hydroxide at 14.8 molar, and you put the test tubes next to each other. Do you remember what happened in the air between the two test tubes? There was a white, cloudy, misty kind of thing. So it makes you want to think, oh, it made a gas there. But why did it not make a gas? Why is that not the case? It was actually wasn't making water. It was making a salt. I'm asking why it wasn't a gas. Let's see. Really hard to do without seeing it.
Was just with energy, you know?
Nope. So you can't see it. I know you guys have used both of these things. All three of you have used both of these things. And I always put them in the hood and I always say, don't do anything. Don't smell these things. They're smelling salts. It'll, feel like a pencil jammed into your nose. So you can't see them, right? They're coming out of the container that they're in, or they're coming out of the test tube that you put them into, or the beaker that you put them into. How come you can't see it? Because it's a gas. You can't see gases. Gases are not visible. Even if you're like, oh, that's a green gas, that's not a green gas. What you're seeing is the formation of water, of liquid of that gas. That's what you're seeing. If it's a true gas, those things are not connected to each other and they are not visible. So can't see a gas. So when Grayson was holding these two test tubes, an invisible gas, because all gases are invisible, was coming out of one test tube and the other one was going into another test tube. And then you saw something kind of look like a cloud. But are you looking at a gas? You can't see gases. So what's the state of matter of the ammonium chloride that was produced? Well, this is ammonium chloride. So what kind of substance is that? And your options are ionic and covalent. No.
Is that ionic?
That's ionic because that's a polyatomic ion. That's NH4, ammonium ion. So it's a polyatomic ion. So this is a cation and an anion. So what do cations and anions make? What do we call that thing? What's the common name for an ionic compound? Salt. So what you're looking at, I'm never going to find that spot. Oh, wait. No. You're going to find a solid is being produced in the air. If you were to be super careful, like clean up that black interior of the hood and wait, that will slowly fall down. And then there'll be like this white dust on top of it, of this ammonium chloride solid. If I were to take you into the chemistry stockroom, every single hydrochloric acid container has this ethereal fine white powder right around the edge. And it's just ammonium chloride that's, none of those containers seal fully. So there's a tiny bit of hydrochloric acid gas escaping. And then there's always going to be ammonia inside a chemistry lab. So they actually form ammonium chloride on the vessel, on the containers themselves. So if you ever see that, like, what is this white powdery stuff on the outside? It's most likely ammonium chloride. And you just wash it off. Not a big deal. Okay, so this is an acid-base reaction. What is not present here? What was not present in that experiment that Grayson had done? Water happened in the air, so there is no water. So this was how Lewis convinced everybody, like, y'all know this reaction. You've all seen it. You all know that as two gases make a solid, and the solid is ammonium chloride, and that ammonium chloride is a salt. And you all know that hydrochloric acid is an acid, and you all know that ammonia adds OH minuses to water, so it's a base. So this is an acid-base reaction, but there's no water present. And they're like, all right, so what do you got? Like, how do you want to change the definition? So he's saying, all right, so first thing we need to do is we need to forget about water and we need to forget about hydrogen ions. No solvent needs to be created. So we can do this wherever we want. And so what I'm going to say is anything that accepts electrons is an acid. And anything that donates electrons to form a bond is going to be a base. So I had said earlier that this definition didn't disrupt the prior two definitions. So let's look at why it didn't. Let's go to Bronsted-Lowry. So this is the classical Bronsted-Lowry chemical reaction of ammonia reacting with water, making water an acid and the ammonia a base. So the ammonia molecule, I've written it with its lone pair of electrons on the nitrogen. Nitrogen has 5 valence electrons. It makes bonds with 3 hydrogens and has a lone pair on top. It's a trigonal pyramidal structure, and then it interacts with the water molecule. What is the nitrogen providing for this chemical reaction? The ammonia in general, but the nitrogen specifically. A pair of electrons. So nitrogen is donating electrons to form a bond. What is the water molecule doing? It's sending something over that's accepting those electrons. So Lewis would say, we still have acids and bases here, and the nitrogen is acting like a base, the hydrogen is acting like an acid, so the NH3 is the base donating electrons, and the H from the water molecule is accepting those electrons, and there's your acid-base reaction. And now I can apply that same idea of electrons being donated and accepted to all acid-base chemical reactions. Why is this super important for us? There's a zillion acid-base reactions happening in your body right now. Do you think you have a bunch of Drano running around in your veins? No, it's too much. So I can't just have free hydroxides added with a salt. That's not possible. But I need a base because there are thousands, if not millions of acids inside. Well, there's thousands of different acids inside your body, and there's only a few bases. The bases themselves all have one thing in common inside your body, and that's nitrogen. So if I've got a nitrogen-bearing compound, that thing is going to act like a base. And if I've got something that can accept the electrons on that nitrogen-bearing compound, then I've got acids. The Arrhenius definition becomes super helpful. I can think about any molecule to establish secure connection.